The meeting should come to order, please. We'd like to continue, and
Hello.
so we can have dinner and.
Hello. Okay.
Right.
So we start now. So let me just summarize in 2 minutes and take any questions if you have some, and then we'll go to the next part of the presentation. Yeah. Okay. So these are the original goals we had. So just to review, I think we did very well putting together this toolkit. It was thousands of lines of code, and it wasn't very clear that we'd be able to get this completed. We built an initial Czech English SMT system, and Jan presented results on not just the baseline system, but actually we had time to do some improvements and do a very initial evaluation of those improvements, which is a little bit beyond what we had expected to do there. We got lots of plots involving perplexity, but since we just got the decoder hooked up with the Giza last week, we haven't had time to do much human evaluations, but there's very important stuff to do there. So we didn't quite finish this part. We expected to do some improvements over the baseline Model 3 system, and you can see the types of things we did. So the faster training was actually critical in support of all these other things, like being able to do MT in a day, being able to do these check prime experiments repeatedly and to do this kind of testing, and to do some of the dictionary and cognate work that Mike and Noah will talk about later. And so we could do all these experiments very quickly, and so we were actually able to do more on this point than we thought we'd be able to. And surprise, I think that worked out pretty good. Okay, so just to give a feel for future work in this area. So long term, when we look at sentence pairs like this, we'd like to be able to come up with better explanations of these translations. And these, instead of revealing Model 3 here, we could be revealing all sorts of things that involve things that are actually much more understood now than when the IBM project ran. So how to get syntactic parses, how to do word sense disambiguation, unsupervised, building in parts of speech, and so on. So that's sort of a longer term goal. In the medium term, there are really interesting projects to do with context-dependent transformation. So under what circumstances does true translate to faux? You can start to think about this. Is the word deny an important thing there? Yeah, probably so, but it probably depends on what deny translates as also. So if you could come up with a better explanation of how sentences translate, you're going to get a better perplexity and hopefully better translations. And so that's kind of medium term. And short term, we have 2 presentations of proposals for follow-on research, and this is going to be merged with the undergraduate presentations in this case. So the first proposal will be from Franz Ock, who is a graduate student at Aachen, and he will be proposing to work for a year of support for a graduate student. And Noah Smith and Michael Yar will be doing a kind of unique proposal for a joint request, which would fund part-time research half-time research during the year, summer support, and travel support to go to conferences. So I'll just turn it over to these guys. So Franz, you will go first.
Okay. So once again, the 3 main disadvantages of Model 3. So one I already mentioned in my first talk are the absolute distortion probabilities, and I developed during the workshop some kind of Model 4 which allows for relative distortion probabilities. But the difference between this Model 4 and the complete Model 4 is that it's independent of word classes. And it seems to be really important to make a complete Model 4, as normally using the simplified Model 4, it's very highly probable that the alignment is monotone. But very often, translating between French and English, it's necessary to make inversions for adjective nouns. So for example, this French expression, it's translated by Weaver, by the current version of Weaver, by charges magical, but should be magical expenses. And the same thing for this expression. So, and the simplified Model 4 could not model this appropriately. but the complete Model 4, which I will show later, is able to handle this. The next disadvantage is that it's deficient. It's not clear, looking at the cross entropy, whether the model is really better than the previous models, models 1 and 2. So it would be nice to avoid this deficiency, only because the model then gets nicer. And it's not clear if this really helps translation quality or things like that, but from the aesthetic viewpoint, it's nice to have non-deficient models. And a very big problem, maybe the biggest one of these, is that all the IBM models from 1 through 5 only allow for single word translations. So it's not possible that a French word is aligned to a whole bunch of English words. And this is necessary. So also a translation of Weaver, this is translated by let fair, but should be let us be fair. There must be some component which allows to group English words together. Or here's an example of German. The word übermorgen is translated by 4 English words, and there are very many German word compounds which could not be handled by any of the IBM models, because they always generate a huge number of English words. So what I suggest is to make a complete Model 4 implementation, so to integrate the dependency on word classes, which then allow to model the, for example, adjective-noun inversion, or to predict moving of modifiers and so on. So the complete Model 4 is, the formulas are very similar. The only difference is that there is now a dependency on the word classes. And so both the models, Model 3 and Model 4, are deficient. Model 3 is deficient because words can be moved on top of each other. Model 4 is qualitatively even more deficient, as it's possible to position words before the beginning of a sentence and after the end of a sentence. And the Model 5, which is described by these equations, something missing, overcomes this problem by doing some tricky calculations. So I also suggest to make this. And but the big problem also is that all the IBM models, Model 1 to 5, do not have a phrase component in it. And what I've done in my thesis after in Erlangen and further developed in Aachen is the alignment template system, which is a statistical machine translation system, example-based machine translation system, which learns from parallel corpora, and it's based on the IBM Model 2, or an extension of IBM Model 2, the HMM alignment model, which also includes relative alignment probabilities, not distortion probabilities. But the major difference between this approach and all the IBM approaches is that there is a basic level of phrase alignment in it. So there are 2 different alignment levels: a low-level word alignment and a high-level phrase alignment. And using this, it's very often much easier to translate idiomatic expressions. So for the alignment template system, for example, these translations are not a problem. And the same is for some of these, because they are simply treated as a unit and translated as a unit, and then it's possible to make these reorderings. So it's important, or I claim it's important, to include a phrase, somehow phrases or sequences of words, or in the translation model. And because it's the restriction of the IBM models is that it's only one-to-many translations. It's not possible to make non-compositional translation, and there is no context in the translation model. And one possibility to do this is the system I developed, the alignment template system. But I think this system has a disadvantage that it's based on on IBM Model 2 or some very simple alignment models. It does not include fertilities, and it includes a lot of heuristics which make it impossible, for example, to calculate the cross entropy. So another solution to integrate phrases in the translation would be to follow the idea suggested in the section 6.3 of the IBM paper to model multi-word septs in English. And so there must be then some mechanism the possible number of multi-word septs would be very huge. So there must be some mechanism to extract possible candidate multi-word septs by doing, for example, something like in the alignment template approach, where I simply look at all aligned phrase pairs in an aligned training corpus, which is aligned by HMM alignment model, or by analyzing the inverse translation model. So it's possible to, if one translates from English to German, as an alignment model, if translating from English to German, then it's possible to represent that number of English words is aligned to one German word. And by analyzing this inverse translation model, I think it's possible to generate such candidate English multi-word sets. And then it's necessary to extend the statistical models to include an additional sept level in the statistical model, where in the first step is then that for English words is decided which words should be grouped into bigger units, and then not the words have all these fertilities, distortions, translation probabilities, but the septs. And yeah, so this is my proposal, to re-implement 4 and 5, to have a baseline systems, to make the corresponding learning curves, to develop a method for extracting candidate multi-word septs, to implement this really as a statistical model, a training algorithm for this, and also a decoding algorithm for this. Questions?
Oh, I have a very fast question, which was the thing about Dan's non-compositional compound work, and where, if at all, that would fit into this thing.
Yeah, so I think we did in Aachen also do some similar things of Dan's work. And the huge difference between the two things is you mean the alignment template system or the thing I suggest? So for the thing I suggest, it would be one possibility to generate candidate phrases. But doing in comparing with the alignment template system, it's so that using this method there is a small number of phrases are found. If you extract all aligned phrase pairs from the corpus, then you have a much bigger number of candidate translations. So it would be one possibility to do this. Yeah.
This Donau ship, etc., is just the insanity of the German orthography. I mean, after all, you could have Donau. In any sane language would have Donau as first word and Dampfschiff as second, etc.
Yeah.
So that's not the problem, because you can certainly do the morphological analyzer, chop it up into individual words, and then you have 5 words. And,
yeah, that's true. So this would be a possibility for some of the phenomena which I want to solve would be another possibility. But making it in the statistical model would be another one.
yeah, but I mean, these compound words are formed on the fly, right? They are not in the dictionary, for instance. I mean,
Yeah. So this example is not in a dictionary, but yeah.
They are just it's a rule of grammar. It's not a word.
But I think sometimes the rules of forming this could be quite complicated. So also the splitting sometimes is not unique, and so. Yeah.
I have 2 points. One addresses your thing directly. An example from Spanish is a word like dámelo, which means you give it to me. Okay, single word. Okay, and you can write these formulas and tactic rules in the wall to decompose it, but it takes you a long time. Of course, Spanish is a big language, so you might as well do it, but for rarer language, you might want to think about it.
Yeah, but you would
Good
never
argument.
get enough statistics on such a long hard to get enough statistics.
The other point here is that you seem to be rediscovering part of the example-based machine translation or generalized example-based machine translation.
Yeah.
So a lot of what you're doing is very similar, for example, what Ralph Brown has been doing in finding phrasal level matches, putting phrases with some variability inside of them.
Mm-hmm.
You put that soyez, not just soyons, and then in your example, morphological variations or some other minor variation, but the main part of the phrase still aligns. And then you can have a one-to-one mapping of phrase to phrase, semi-idiomatic or fully idiomatic phrase to phrase instead of having many-to-many mapping. And it simplifies.
Mm-hmm.
If you do the canonicalize the phrases in the beginning, it simplifies the number of possible mappings that you're worrying about later on.
Mm-hmm.
It's basically the same kind of idea of finding matches with kind of dynamic programs and so on.
Once the toolkit is completed according to your plan, if one were to dust off the evaluations from the machine translation project that IBM participated in, and
Sorry, dust off? What?
Recycle.
Okay.
Read it off, whatever media. If we repeated that evaluation and with your improvements turned off, would we expect to get the same results that IBM had got?
Better results.
I said with your improvements turned off.
With the improvements turned off, well, so this does not include all the.
Completed and combined with what's been done this summer, will there be any major missing components that were present in that IBM system, or will the whole community be able to start with the baseline of reproducing their results on that?
So in the IBM system, there were still additional things. So they had, for example, this word sense disambiguation by looking surrounding words, and special thing for integrating a dictionary, but maybe the thing that will be presented afterwards is even better than the IBM suggestions. So so this will not include the whole thing that IBM did, but a very important improvement, I think, to incorporate phrases or many-to-many alignments, not only one-to-many.
Also, the coder is not exactly the same. So, can't get exactly the same.
When you mentioned word classes, when you were talking with on one of the previous slides, where are you planning on getting the word classes from?
By making maximum mutual information between adjacent classes,
Sorry?
sorry,
You're going to use the same mutual information hierarchical clustering?
not hierarchically. The Knies-Anai one, where you have a fixed number of classes in the beginning, a random initialization, and then you move words around and improve maximum likelihood
Do you
criteria.
think that could, given that there's a huge amount of work going on by various people on different ways of clustering and of obtaining distributional word classes and combining knowledge-based word classes with distributional ones, do you think you could do that in a modular enough way that other people can plug in different word class models and
So-
plug it straight into this?
This shouldn't be a problem. So if it's only a mapping from the complete vocabulary pair size English-French to a smaller number. So in the IBM paper, they had 50 classes for English, 50 for French. So 2,500 numbers where one thing could depend on.
So it's just a
So-
suggestion that you actually put in an interface for that so that could work.
So in fact, I also worked already on making bilingual word classes. So making word classes which are correlated between source and target language. Because if you have maximize source language word classes, target language word classes, these are very different. And it's possible to make the same thing maximum, not maximize on bigram language model, but a translation model. And then you have correlated word classes. So this would also be interesting to apply here then. Okay, so.
All right. Can everyone hear me? I am Noah Smith of the University of Maryland, and Mike Yar and I will be co-presenting on some preliminary experiments that we have done and some ideas that have been planted in our minds, and our hopes for the future in making statistical translation models smarter. So let me start off reiterating a couple of the problems with the baseline translation model. First of all, it's been mentioned before that rare words collect garbage. There's not enough co-occurrence data for words that don't occur very often in the corpus, and so they'll align to almost anything. We have noted over-adaptation to the training corpus. There's a certain point at which test perplexity begins to rise after a certain number of iterations of training. Also, the vocabulary is limited to words seen in the training corpus. So if in the decoding step you were to come across a word you hadn't seen, there would be no basis for deciding what to do. Another couple other problems. First of all, conditional probabilities don't tell the whole story. This is sort of a philosophical problem that we have. Mike will talk a little more about this in a few minutes. And lastly, the IBM models provide a very low level of analysis of the actual translation process that we think is inappropriate. I'm going to discuss one approach to helping these first three problems, which is to use dictionary information. So this quote from Fred came from the beginning of the workshop, and so here we are. I'm a linguist, and we're using dictionaries. We have at our disposal a Czech English dictionary, which is lemmatized using the same scheme as used on the corpus. And so there's some statistics. We had to do a little bit of tweaking to the dictionary to make it fit our methods, but this tells you how relevant the dictionary is to the actual corpus. One of the key things to note is that for the corpus size which we used, which was a training corpus of 38,000 Czech to English aligned pairs, the dictionary, when you add on, in one case, 86,000 entries to the dictionary, this adds a whole lot more data. So we're not quite sure what would happen were the corpus much larger. In any case, I'm going to discuss the use of the dictionaries, but first I want to focus on some of the shortcomings. So there are three types of tokens which we can find in parallel texts that demonstrate that you can gain information about translation by looking at the words themselves. For example, technical terms, medical terms tend to be very frequent in our Czech corpus. Also proper nouns and words with common roots and borrowed words. And we're obviously not the first people to notice these things. Simard et al., 1992, Church 93, and Fung 94 are all worthy of mention here. Another point is that these words are corpus specific. So if we can glean this data from the corpus itself, then it's going to help us in ways the dictionary can't. So how do we find cognates? From here on in the talk, I'm going to refer to cognates as any words that, one word in one language, another word in another language, they look alike and they have the same meaning. So what do we mean they look alike? There's a standard measure of string similarity, LCSR, which stands for lowest common subsequence ratio. And this year, Tiedman from Sweden gave some methods for modifying this LCSR to account for language-dependent character mappings. For example, the Czech K maps very often to the English C in cognates. So these methods that he uses involve weights for any given Czech character to any given English character, beyond the LCSR weights, which are 1 or 0. And these mappings can be learned from a set of known cognates. But we don't have a set of known cognates. In our case, we do have a dictionary, and we also have a corpus. I did some experiments. This is my methodology for determining cognates using the dictionary and the corpus. So I trained the weighting function on the entire dictionary, and there was a lot of noise, obviously, because everything in the dictionary was not a known cognate. In fact, most things were not. But when I filtered and took the top scoring pairs from the dictionary and pretended that they were known cognates, which is very likely true because they looked very much alike. I retrained the weighting function and then scored all the co-occurrence pairs from the corpus. So I should note that there are some restrictions on what can be scored using Tiedeman's methods. You will not score an English word against a Czech word if their length ratio is any more than 7 to 10, and you don't worry about words that are less than 4 characters. So we came out with something on the order of 1 million cognate pairs, ranked from a score of about 0.6 down to about 0. And here they are at different intervals. So you can see the top, they're exactly the same, and as you move down, you'll notice at about 0.3, intuitively, they're not cognates anymore. And I say that, and I'll emphasize, intuitively, they're not cognates anymore. When we actually did the experiments, it seemed that using cognates all the way down to a score of 0.15 was the most helpful. So in any case, thresholding is important. You don't want to use rotten pairs, they're not going to help you. But some rotten pairs do help you. We don't know why that is yet. So, okay, here's how we use the lexicon. From here on, I'm going to use the term lexicon to refer to any set of a priori mappings between the two languages. The dictionary and or these cognates, which we've derived. So the 3 experiments were to seed the Model 1 translation table, second, to filter the counts in the initial Model 1 iteration, and I'll explain that further. And Mike is going to talk about adding the lexicon to the training corpus in the spirit of Brown et al. 1994. The corpus that we used for all of these experiments, like I said, was a 50,000 K Czech to English set of sentences, and the Czech was lemmatized. The training schedule that we used was 5 iterations of Model 1 training, 5 of Model 2, and 10 of Model 3. And our evaluation metrics are test perplexity and alignments. So, seeding is a very simple way of doing this. In the baseline, Model 1 training begins with a uniformly distributed translation table. So, the probability of any given Czech word given an English word is 1 over the Czech vocabulary size for all pairs. In our experiment, we changed this so that word pairs that occur in the lexicon receive a factor of C more probability than the other pairs. And we used values of C ranging from 2 to infinity. And by infinity, I mean pairs that did not occur in the lexicon received an initial probability of 0. So, here are the results looking at test perplexity. And I had a pen here. You can see here, that is the so-called weight factor of infinity. There's a limit to how much you can improve test perplexity here. And the reason there's a limit is because the seeding is being washed out. So we need something a little bit stronger if we want to get a better improvement. So the dictionary constraint is my term for a redefinition of co-occurrence for Model 1's first iteration. In the baseline of Model 1, the first iteration counts co-occurrences as follows. An English word and a Czech word co-occur whenever they appear in parallel sentences. When we add the dictionary constraint, we redefine co-occurrence in this way. In a parallel sentence E and C, E sub I and C sub J co-occur if either they are in the lexicon together, or each of them does not occur in the lexicon with the words in the opposite sentence. I have an analogy for this. You have the Czech words, which are the women at a dance, and the English words, which are the men at a dance, and the lexicon is a list of the married couples. The married couples are only going to dance with their spouses, and everybody else, the singles, are going to mingle. So that's basically an explanation of how it works, and here's a picture. So the top is the baseline, and everything dances with everything, but when we put the dictionary constraint on things, the lexicon pairs, all, to, for, and best, mieux, are constrained.
I guess a better explanation is that some married people might be in the party but not with their spouse.
I'm sorry, I can't hear you. Yes, that's true. Also, as a side note, an English word could occur in a lexicon with two of the French words in the sentence, so we do have a potential for polygamy. Okay, so here are some results with the dictionary constraint, and you can see a marked improvement. There are three different lexicons represented here. The one that did the worst was just the cognates, thresholded at 0.15. Directly below that, using the original dictionary, and lastly, a merged list of the dictionary and the cognates with a score of 0.15. We did testing for different thresholdings of cognates, and this did the best. Like I said before, we're not sure why, because intuitively, what's a cognate seems to stop at about 0.3. And Tiemann had the same result. 0.3 seems to be a good threshold. I also said we'd be looking at alignments. So the top here is a baseline alignment. Let me move this down. And the bottom is an alignment using the dictionary constraint. And you can see, first of all, that gigantic, that's a dictionary pair right there. And seismic, that's a cognate. And up here, you can see the rare word syndrome. Seismic is a garbage collector. Also killed. There's a dictionary pair. So obviously, these are helping. And now Mike is going to talk about our third experiment and a few other things.
Okay. Okay, I'm gonna pick up right where Noah left off. He discussed the first two experiments we had, which were seeding and restricting the count collection. And the next thing we tried was adding lexical information to the end of the training corpus, which was similar, at least on the surface, to what Brown et al. Did in 1994. And so the idea is basically just that you take your dictionary entries and make them into very short sentences and just add them onto the end of the corpus. And this approach has a number of advantages. First, the information is present for all iterations of the models, however long you want to do it, unlike the other two approaches, which tend to get washed out because they're only present for the first iteration of Model 1. Secondly, it's very easy to accommodate multiple word entries because it just makes longer sentences. Third, it's possible to vary the weight of the entries based on different things. And fourth, it's very easy to integrate into any training software that you happen to already have, just because it involves only a corpus modification.
So, excuse me, if a word has 5 translations, then you have 5 sentences?
Exactly.
5 sentences.
Okay, so what can we put in the lexical edition? Is the question. We have a couple different things that we can vary. One is what to actually add in what part of the lexicon to actually add to the training corpus. We can use all lexicon entries or only entries which actually co-occur in the training corpus. And the second thing we can vary is the weighting function. And we tried a number of different ones. Our baseline was just a uniform where we assigned the same weight to all dictionary pairs. We had an inverse linear weighting function and an inverse exponential weighting function, and these were both inverse with respect to frequency because we expected the dictionary to have better results on less frequent words, so we wanted to give those dictionary entries a higher weight. Okay. And here are the results of the dictionary editions. And you can see that there is a substantial impact on test set perplexity. This is actually, it's reduced by nearly half. It went from 2,000 to nearly 1,000. And what these different lines are the top one is dictionary with only co-occurrences. The next one is dictionary only, and then we have 2 different cognate thresholds below that. And so, as Noah said before, the cognate threshold of 0.15 seemed to produce the best results. And there were alignment results with this, which were very similar to the ones that Noah showed before. So just a brief recap of the results of the dictionary experiments. We produced significant reductions in test set perplexity and noticeable improvements in word alignments. These are both positive results. And interestingly, the best results in word alignments came at the cognate threshold of 0.3, which produced a higher test set perplexity. So it's worth investigating why this happens. Intuitively, we'd like to think that it's because this is actually where the real cognates stop. And it's worth investigating why test set perplexity continues to drop with more additions. And we found that cognates can be found starting from only corpus co-occurrences. It's not necessary to have a dictionary, strictly speaking, to generate cognates. Another approach that we can take is to use symmetric generative models in place of IBM's earlier models. The motivation for this is that, firstly, that IBM models only look at conditional probabilities when joint probabilities may give us a better model, the data that we're trying to represent. So our objective is to take advantage of joint probabilities through a symmetric model. Again, this is IBM's source channel model. Just very briefly, you start with a bag of English words, apply some transformation to them, and produce French words. And so the way you try to model this is you collect counts over all pairs to try to estimate probability of F given E for each English word. A more abstract model, on the other hand, would model pairs of English and French words generated together at the same time. This can be imagined as actually you're not generating words at all, but you're generating concepts which have a representation in each language. And this results in a one-to-one matching between words. And so, in order to model this, we collect counts over not all alignments, but only the best alignment, the optimal assignment between the two sentences. And this actually reduces very nicely to a well-known problem from graph theory known as the maximum weighted bipartite matching problem. And it has an optimal solution, and has been studied. But there are some issues to be addressed with this approach. Firstly is initialization, because maximum weight bipartite matching is meaningless if all the links have the same probability, because it's completely random in that case. So it's necessary to bootstrap the model somehow. There are the basic method you would want to use to do this is to use co-occurrence data in some way. The simplest method is just to run an iteration of model 1 and get initialization data from that. But we could also use dictionaries and cognates to do this, or any one of a number of different statistical methods. And the second issue is efficiency, because this is a harder problem than merely collecting co-occurrence counts. But it has a higher big O notation, but it has, the upside is that it converges faster in fewer iterations. And these more abstract models have a number of advantages. They are at a higher level than IBM models, a more abstract level, and so because of this, they have more general applicability for other domains such as cross-language information retrieval, concordancing, bilingual lexicography, and also computer-assisted language learning. It's also a relatively new approach. It's been pioneered recently by Dan Melamed in his thesis in 1998. And furthermore, it would be interesting to extend this model to account for other linguistic structures such as word order and phrases. And the framework is sufficiently general that this is possible, and it's a worthwhile pursuit. Okay. Now we will give our proposal for future research.
Just a fast question on what you were just discussing.
Sure.
Is there just the conceptual representation appear as a hidden variable in the framework?
Yes, it's only manifested as bags of words, basically, as pairs of words, or some concepts might not have representation in some languages, so it could be a word in a null.
Okay, I was just wondering about the potential applicability to word sense disambiguation in a framework like EuroWordNet, where you actually have an explicit representation of concepts and words from multiple languages mapping into it.
That's an interesting idea. It would be worth exploring.
How do you handle the many to one mapping?
The many that's not something that we've done so far. We've only done one.
1 to 1 and 1 to null?
Yeah, 1 to 1 and 1 to null. But
The many-to-many problem can actually be developed from this. The symmetric model that has been described so far is couched in terms of concepts. So it's conceivable that a concept could be multiple words.
But there's a number of hypotheses that you will have.
yes, this is the problem that that's the basic framework that we would use to do multi-word phrases, but we haven't worked out any of the statistics as of yet.
Okay, so. All right, so our proposal for future research is to try, is to try to improve statistical translation models using two methods. First of all, we'd like to explore unsupervised induction of cognates, specifically translingual grapheme-phoneme mappings, continuing the work of Knight, 1997, and we'd like to focus on languages with different orthographic systems. In particular, languages that like to corrupt each other. For example, Japanese and English, or Hindi and English. Another interesting area of exploration is the difference between phonetic and graphemic cognates. For example, the English word commencement is a cognate with the French word commencement. And they look the same, but they don't sound the same. Whereas the English word Coca-Cola is a cognate with the Chinese Coca-Cola, which doesn't look anything like the English writing of Coca-Cola. So that's one side of it.
The other side is extending the symmetric paradigm to new levels. Symmetric generative translation models at a higher level of abstraction, implementing and extending the work begun by Dan Malamed in 1998 to include, to go as far as we can with it basically, to include phrases, which is definitely possible, and basically to implement the ideas that have been set forth and work with them.
Are there any questions?
Did your cognate match your preferred things that are roughly the same length? And is it possible that your sort of lousy cognates are actually picking out things that co-occur that are also about the same length, and that's why they tend to be good matches as opposed to connecting with something else in the sentence, which is an even more lousy cognate because it's too long?
Okay, so the cognate matching method that I implemented from Tiedemann was his simplest method. He discussed 3. And basically what this method does is it tries to align single consonants to single vowels, which isn't really that intelligent, but we got reasonable results. His next smartest method was to align consonant clusters and vowel clusters to each other. So in a case like that, word length would not be quite as big of an issue. These are questions that need to be explored.
Have you considered the problem that some of these cognates are not cognates at all, although they may have come from the same root or meaning to languages?
Yes, we're well aware of the phenomenon of faux amis, but we're allowing some noise. Essentially, we're assuming that the number of faux amis is far outnumbered by the number of real cognates, especially because most of the cognates we're finding tend to be names, places, technical terms, and so on.
And the results seem to support this.
I should add to that that when you're actually dealing with a parallel corpus, a translator will avoid translating a word with a photosemia that occurs in another part of the sentence.
Right.
So there's automatic compensation for that.
Okay, so I apologize for going too late. Usually our talks finish really earlier, so I had too much faith. My part went over too. But if there's any questions for general discussion, we can open it up. Or if you're had enough, okay.
How much do you think of this technique of doing statistical alignment is taking advantage of the fact that these are, at least for things like Hansard, are translated in an almost automatic way by almost the same people using the same style? I mean, maybe that's a good thing to pick up that style that they're doing. And while if you did it for something like newspapers, or if a parallel corpus could exist for newspapers, it would be much harder.
Yeah,
Possibly the Czech fiction one would be harder because it's maybe more imaginative in its translation.
They just need more data.
I think these Czech translations are definitely more free than the Hansard, but just like this true and false, I think there are much worse cases than that. That's sort of a funny case. But the non-funny cases are just things translate completely differently. And I don't know how many translators these guys use. I don't know whether it's an effect of using multiple translators, but even if there was just one, I can just see crazy translations. And there's so many, singulars translate as plurals all the time. It's just strange, and there's so much strange stuff in there. And that's really the next step, is to sit down for hours and hours and hours and pick up where these guys left off and stare at this data and come up with better theories.
Did the stuff these guys were just discussing, did the evaluation get compared against the standard model 1, 2, 3? You measured, I see, you showed test sample complexity, right?
The baseline was the highest one, at the very top of the graph.
Okay. So, and I'm sorry, what was the baseline?
The baseline was just standard model 1, 2, 3, like you said, without
no
dictionary
dictionary
additions.
So we had a lot of dispute at the beginning about this test perplexity. Okay, there's a very small minority of us who like test perplexity and think it's great, and there's other ones who think this is the wrong measure. Went back and forth. There's really interesting discussions over these graphs. And in practice, in the 6-week workshop, we didn't connect up the decoder with the Giza until the very last week. So we couldn't have done any experiments and gotten any results without this test perplexity. Now we need to establish that they also showed alignments, right, that showed things seem to be getting better. But we got to show the whole decoding, so we have to go the whole way. But in this workshop, it turned out to be a great measure.
And evaluation is a whole separate issue that may deserve a workshop of its own. But have you got a plan for how you're actually going to evaluate this stuff?
Yeah, we discussed that a whole lot too. It's easy to sit back and talk about it. It's hard to do it, but everybody's got their 50 best ideas about how to do translation evaluation. It's just that everybody's got a different order, so you can talk for hours and hours. Yeah, I wish we had a picture of this web-based tool. It's really nice, and it can be configured in many different ways. And we could deliver it over to the Czech Republic, and they did it. So, however, whatever we decide, I think that's the best delivery for it. But 1 through 5 scoring, I think is reasonable. Comparing two different systems, which one's better, the old system and the new system, is another way to do it, and to see how much improvement you're making on how many sentences. There's many ways to do it.
There's a Moore's law component in fast training compared to the IBM system, maybe a factor of 100, 120 or so. The question is, what's your sense about the utility of lots of extra computing in pushing this technology?
Sure.
Actually, there's not just the speed, right? There's also things like memory, memory increases that feed off each other. So one thing we did, I don't know if we stressed this enough, in addition to the speed up in electrics to train a model, we also drastically brought down the amount of memory it takes to complete the computation, right? And once you get below a certain threshold, you stop thrashing it. And that has a huge impact. So actually one thing we were successful in doing was training on 1.5 million sentences or something. without any replacement of words with the unknown token, right? So the entire vocabulary of the Hansard, which was just qualitatively not possible before. And in this particular case, I was actually watching it as it was computing. Up to about 1.2 million words, sentence pairs, sorry, there was no swapping. Right? After that, it started swapping, so of course the time goes right up. Yeah, I mean, all these things feed off each other.
Yeah.
The increases are.
So that was something that IBM people couldn't do. They had to restrict their vocabulary to something like 40,000 words. So this is a big deal.
That's one flavor. The real question was projecting out into the next year or two.
This is completely parallelizable is another point. So we had great big plans to use all our 10 machines all running at once. It was going to take 24 hours, but all of them working together in 24 hours to complete an experiment, and by God, we come in the next morning and then have our results. We didn't have to do any of that in the end. It was great. Everybody ran their own experiments on their own machines and didn't interfere. It was nice.
Okay. I don't need it. Well, all right. Okay. So this is the end. I thought I will tell you certain things. I am very refreshed by the fact that Kevin reverted to the old technology. And you know, this whole march of technology which forces us to use machines like that is really deplorable. Except when James uses it to make things fly, all right? So then, all right, he could never do that. I was going to tell you another story about Norbert Wiener. Actually, I was at MIT when Norbert Wiener was still there, but my professor, who I loved, is somebody named Guillemin. And Guillemin is a founder of something called network theory, and he is the professor of all the famous people. I mean, Shannon and Fano and Zadeh, and everyone is his student. So anyway, so during the war at MIT, there was something called the radiation lab, and they were solving problems, radar problems. And Guillemin told me the following story, that one day, you know, he was working very hard and things were completely, you know, he didn't know how to solve this problem, etc. And he met Norbert Wiener, who was working on the same project. And as Guillemin remarked, Norbert Wiener thought that he won the war single-handedly. So anyway, he asked him about this problem, and MIT, I don't know if any of you were at MIT, but it had classrooms where the blackboards were all on all four walls, all right? So Norbert Wiener says nothing to it, and started writing on the first blackboard, and kept writing and writing, and Guillemin was sitting there, and when Norbert Wiener got to the door, he walked out, and Guillemin never saw him again. So he was a very famous man in my time. I mean, he wrote a book called Human Use of Human Beings, and he's the author of the term cybernetics. You know, there's a book called Cybernetics, etc. So,
but did he solve the problem after writing around?
Nobody knows, but the war was won, right? So maybe by not solving it, we won it. Who knows, right? Anyhow, I was going to say that some people didn't know where we have the dinner. So the dinner is in front of the president's house. There's a lawn there. I don't know how to describe it. It's in that direction. You will see.
That direction.
All right. You mustn't walk through walls anyway. And tomorrow we'll have a lunch. And at that lunch we will distribute party favors. So those who don't come won't get them. And we will also announce the winners of the contest. And I don't know, I was very happy about this workshop. It used to be that the workshops were completely dominated by speech, and that was kind of boring. And last year we had some no-speech problems, and this year speech is only 1 of 4, and I think we should keep it that way. And okay, that's all. So I'm glad you came, and we'll talk again at dinner, and we'll talk again tomorrow lunch. So thank you for coming and working hard and doing us proud.